Metal detector technology is a huge part of our lives, with a range of uses that spans from leisure to work to safety. The metal detectors in airports, office buildings, schools, government agencies, and prisons help ensure that no one is bringing a weapon onto the premises. Consumer-oriented metal detectors provide millions of people around the world with an opportunity to discover hidden treasures. In this video, you'll learn about metal detectors and the various technologies they use. Our focus will be on consumer metal detectors, but most of the information also applies to mounted detection systems, like the ones used in airports, as well as handheld security scanners. Metal detectors use one of three technologies: very low frequency (VLF), pulse induction (PI), beat frequency oscillation (BFO). In the following sections, we will look at each of these technologies in detail to see how they work. VLF technology. Very low frequency (VLF), also known as induction balance, is probably the most popular detector technology in use today. In a VLF metal detector, there are two distinct coils. Transmitter coil. This is the outer coil loop. Within it is a coil of wire. Electricity is sent along this wire, first in one direction and then in the other, thousands of times each second. The number of times that the current's direction switches each second establishes the frequency of the unit. Receiver coil. This inner coil loop contains another coil of wire. This wire acts as an antenna to pick up and amplify frequencies coming from target objects in the ground. The current moving through the transmitter coil creates an electromagnetic field, which is like what happens in an electric motor. The polarity of the magnetic field is perpendicular to the coil of wire. Each time the current changes direction, the polarity of the magnetic field changes. This means that if the coil of wire is parallel to the ground, the magnetic field is constantly pushing down into the ground and then pulling back out of it. As the magnetic field pulses back and forth into the ground, it interacts with any conductive objects it encounters, causing them to generate weak magnetic fields of their own. The polarity of the object's magnetic field is directly opposite the transmitter coil's magnetic field. If the transmitter coil's field is pulsing downward, the object's field is pulsing upward. The receiver coil is completely shielded from the magnetic field generated by the transmitter coil. However, it is not shielded from magnetic fields coming from objects in the ground. Therefore, when the receiver coil passes over an object giving off a magnetic field, a small electric current travels through the coil. This current oscillates at the same frequency as the object's magnetic field. The coil amplifies the frequency and sends it to the control box of the metal detector, where sensors analyze the signal. The metal detector can determine approximately how deep the object is buried based on the strength of the magnetic field it generates. The closer to the surface an object is, the stronger the magnetic field picked up by the receiver coil and the stronger the electric current generated. The farther below the surface, the weaker the field. Beyond a certain depth, the object's field is so weak at the surface that it is undetectable by the receiver coil. In the next section, we'll see how a VLF metal detector distinguishes between different types of metals. VLF phase shifting. How does a VLF metal detector distinguish between different metals? It relies on a phenomenon known as phase shifting. Phase shift is the difference in timing between the transmitter coil's frequency and the frequency of the target object. This discrepancy can result from a couple of things. Inductance, an object that conducts electricity easily, is inductive, is slow to react to changes in the current. Resistance, an object that does not conduct electricity easily, is resistive, is quick to react to changes in the current. Basically, this means that an object with high inductance is going to have a larger phase shift because it takes longer to alter its magnetic field. An object with high resistance is going to have a smaller phase shift. Phase shift provides VLF-based metal detectors with a capability called discrimination. Since most metals vary in both inductance and resistance, a VLF metal detector examines the amount of phase shift using a pair of electronic circuits called phase demodulators, and compares it with the average for a particular type of metal. The detector then notifies you with an audible tone or visual indicator as to what range of metals the object is likely to be in. Many metal detectors even allow you to filter out, discriminate, objects above a certain phase shift level. Usually, you can set the level of phase shift that is filtered, generally by adjusting a knob that increases or decreases the threshold. Another discrimination feature of VLF detectors is called notching. Essentially, a notch is a discrimination filter for a particular segment of phase shift. The detector will not only alert you to objects above this segment, as normal discrimination would, but also to objects below it. Advanced detectors even allow you to program multiple notches. For example, you could set the detector to disregard objects that have a phase shift comparable to a soda can tab or a small nail. The disadvantage of discrimination and notching is that many valuable items might be filtered out because their phase shift is similar to that of junk. But if you know that you are looking for a specific type of object, these features can be extremely useful. PI technology. A less common form of metal detector is based on pulse induction, PI. Unlike VLF, PI systems may use a single coil as both transmitter and receiver, or they may have 2 or even 3 coils working together. This technology sends powerful, short bursts, pulses, of current through a coil of wire. Each pulse generates a brief magnetic field. When the pulse ends, the magnetic field reverses polarity and collapses very suddenly, resulting in a sharp electrical spike. This spike lasts a few microseconds, millionths of a second, and causes another current to run through the coil. This current is called the reflected pulse and is extremely short, lasting only about 30 microseconds. Another pulse is then sent and the process repeats. A typical PI-based metal detector sends about 100 pulses per second, but the number can vary greatly based on the manufacturer and model, ranging from a couple of dozen pulses per second to over 1,000. If the metal detector is over a metal object, the pulse creates an opposite magnetic field in the object. When the pulse's magnetic field collapses, causing the reflected pulse, the magnetic field of the object makes it take longer for the reflected pulse to completely disappear. This process works something like echoes. If you yell in a room with only a few hard surfaces, you probably hear only a very brief echo, or you may not hear one at all. But if you yell in a room with a lot of hard surfaces, the echo lasts longer. In a PI metal detector, the magnetic fields from target objects add their echo to the reflected pulse, making it last a fraction longer than it would without them. A sampling circuit in the metal detector is set to monitor the length of the reflected pulse. By comparing it to the expected length, the circuit can determine if another magnetic field has caused the reflected pulse to take longer to decay. If the decay of the reflected pulse takes more than a few microseconds longer than normal, there is probably a metal object interfering with it. The sampling circuit sends the tiny, weak signals that it monitors to a device called an integrator. The integrator reads the signals from the sampling circuit, amplifying and converting them to direct current, DC. The direct current's voltage is connected to an audio circuit, where it is changed into a tone that the metal detector uses to indicate that a target object has been found. PI-based detectors are not very good at discrimination because the reflected pulse length of various metals are not easily separated. However, they are useful in many situations in which VLF-based metal detectors would have difficulty, such as in areas that have highly conductive material in the soil or general environment. A good example of such a situation is saltwater exploration. Also, PI-based systems can often detect metal much deeper in the ground than other systems. BFO technology. The most basic way to detect metal uses a technology called beat frequency oscillator, BFO. In a BFO system, there are 2 coils of wire. One large coil is in the search head, and a smaller coil is located inside the control box. Each coil is connected to an oscillator that generates thousands of pulses of current per second. The frequency of these pulses is slightly offset between the 2 coils. As the pulses travel through each coil, the coil generates radio waves. A tiny receiver within the control box picks up the radio waves and creates an audible series of tones, beats, based on the difference between the frequencies. If the coil in the search head passes over a metal object, the magnetic field caused by the current flowing through the coil creates a magnetic field around the object. The object's magnetic field interferes with the frequency of the radio waves generated by the search head coil. As the frequency deviates from the frequency of the coil in the control box, the audible beats change in duration and tone. The simplicity of BFO-based systems allows them to be manufactured and sold for a very low cost. But these detectors do not provide the level of control and accuracy provided by VLF or PI systems. Metal detectors are great for finding buried objects. But typically, the object must be within a foot or so of the surface for the detector to find it. Most detectors have a normal maximum depth somewhere between 20 and 90 centimeters. The exact depth varies based on a number of factors. The type of metal detector, the technology used for detection is a major factor in the capability of the detector. Also, there are variations and additional features that differentiate detectors that use the same technology. For example, some VLF detectors use higher frequencies than others, while some provide larger or smaller coils. Plus, the sensor and amplification technology can vary between manufacturers and even between models offered by the same manufacturer. The type of metal in the object, some metals, such as iron, create stronger magnetic fields than others. The size of the object. A dime is much harder to detect at deep levels than a quarter. The makeup of the soil. Certain minerals are natural conductors and can seriously interfere with the metal detector. The object's halo. When certain types of metal objects have been in the ground for a long time, they can actually increase the conductivity of the soil around them. Interference from other objects. This can be items in the ground, such as pipes or cables, or items above ground, like power lines.